of Things. If we had to rewrite the compiler by hand every single time someone came out with an improvement to GCC, then there would be very few improvements to GCC. And finally, I like to think of the actual real physical things you can hold in your hand, like a bottle that holds this water, as the binaries. Sorry. This finished product doesn't contain any information on how to make it. All you can see is some general hints about how it was made. They had some sort of grooving thing come in and make the grooves on the mold somehow. But there's no specifications on, okay, well, we want the diameter of the thing to be this and the pitch on the threads to be that. You can find that by sort of reverse engineering and measuring it, but there's no real authoritative source on this itself. And also, it can only be shared the old-fashioned way. So if I give you this bottle, then, well, I don't have a bottle anymore. So whereas with your source, if I give you the design for the bottle, you can make your own bottle, and then I still have my bottle, and everybody wins. Finally, do you have the source for your CD player? Do you have the source for your computer, your mouse, your chair, all of these things? Essentially, every physical object we interact with in the real world is closed source because you don't have the design files that are needed to make more of these things. Sure, you can look at it and say, oh, well, that's how they did that. I can do that too. What I'm talking about here is people designing something, releasing the source code for that on the internet, and then you, with your machine, can download that source code and then make yourself another copy. And if, this camera doesn't work the way you like it, then theoretically, if you know enough about it, you can get in there, change the source, and then make yourself a better one. And if you're using an open source one, you release that on the interwebs, and then other people can benefit from that as well. So what are the implications of this? Well, first of all, robots are going to take over the world. It's just going to happen. I mean, they're just so cool, and there's so many obvious benefits that it's inevitable. But the thing is that it's up to us to ensure that it happens in a good way. One thing I'd like to say, if anybody ever tells you that technology is neither good nor bad, they're lying. All technology is created with a purposeful intent. AK-7s were made to kill cheaply. Some guy wasn't just like, oh, I'll just put this steel in a certain configuration and let's see what people do with it. So if you're making technology, examine the intent and why you're making this technology. With digital fabrication, we're building tools of creation. These things are explicitly designed to create and build new things, and which is one of the reasons why I feel it's a very beautiful technology. None of this stuff is designed to kill or maim or hurt. It's all about building things to help improve the lives of your friends, your family, and the rest of the humans around you. So, what happens when things go digital? Well, first of all, you can design something in place A, you can email it to place B, and then the person in place B can print it out. You can also do version control. So you can roll back to CUP version 1.2 if version 1.3 isn't, it's leaky or something. Personally, I love version control. It's excellent, and I'm glad someone invented it. You can do easy worldwide collaboration. The RepRap project, which I'm totally obsessed with, is distributed across the globe. I'm in New York. The guy that started it is in the UK. There's a ton of people from Vienna, the Netherlands, New Zealand, Australia. I think we have pretty much someone from all of the major continents and probably every country. Not only that, but because you have the source code itself, you can make as many copies as you want, or at least as you can afford to make. I don't want to beat you over the head, but the idea is that you can work at a higher level of abstraction. That abstraction allows you to get more done in an easier way, much better than you can by hand. And you can scale. So here's an example of that: design in one place, build in another place. My friend Marius Kentel from MetaLab is really kicking some butt here. He designed this twisted star cylinder box, something you could just use to hold, jewelry or doodads or whatever. And he uploaded it to Thingiverse. And then a few days later, another guy by the name of Chris Palmer, goes by Knophead on the internet, built it with his RepRap machine. And so these two people are separated by, I'm not sure exactly far, but let's say 1,000 miles. And they were able to share this design. They're able to essentially share these physical goods without paying any sort of postage fees or anything like that. They just sent it over the internet, and then the other person had a machine, he hit print, walked away, probably had a tea break or something. He's from the UK, so. And then when he came back, he had this excellent little container, and I think he gave it to his wife for a birthday present, so, which is nice. Another cool thing is that with these machines, you can have infinite customization because it's all a digital design. Like, you feed the machine a design, it does it. It doesn't care what the design is. It doesn't say, oh man, there's too many circles in this guy, like, lay off. You can just, you can feed it whatever you want. So I'd like to show you an example that one of our friends, Oskay from Evil Mad Scientist, made. It's a snowflake generator. Let me see if I have it here. So this is just a little processing sketch, and it starts off with, oh no. Okay, yes, giant snowflakes. Okay, so it's pretty simple. If it works. All right, sorry about that. Let me try another one. Okay, so it starts out like this. And you just grab the things on here, and you can just control it to do like crazy things like that. And then when you're done, there's a save button on here. It's down on the bottom. You can't really see it. But this will write it to a vector-based file. And then you can send this to your laser cutter and have your own custom snowflake. And you can create 1 million individual snowflakes. So let's use our brains for a minute here. Imagine you're a manufacturer. You're a manufacturer that makes toy army men. You have to make 1 million of a model of a toy army man in order for the economies of scale to pick in and make it worthwhile to produce. Your constraints are that you have to make each soldier as a solid piece of plastic in order to avoid choking hazards. There are 30 different characters in your army, including the bad guys. Your engineers have come up with 5 different kung fu grips. The designers have come up with 10 different outfits, including different styles of face paint. The weapons designers have come up with 20 different weapons, and each toy soldier could come in any of 15 different positions, so prone, standing, jumping jacks, whatever. That means there are 30 times 5 times 10 times 20 times 15, or 450,000 different combinations. So what do they have to do? They have to choose a few designs and then make 1 million of that single design. With digital fabrication, you can just as easily make 450,000 different toy soldiers, each with a unique pose, weapon, whatever you want. Or you could just make 450,000 of the same toy soldier. I don't know why we would want to do that, but you could. To the machine, it's, like I said, it's all the same file. So it allows you just to customize and have these very unique things that would be tailored to what you want instead of how it's dictated to you by someone else that controls these means of production. Another interesting thing is that you are transformed from a consumer to a producer. If you need a laptop stand, download Eric Skiff's laser cut laptop design and make yourself one. And then you can hold your laptop up on a stand and you don't have to get it from anybody else. If you want to give your friend a copy, you can just make him a copy, or you can sell it if you want. Once you do that, you're no longer someone that just has to depend on other people to make these things for you. You become a producer. You become someone who's self-reliant and can create the own things that you want or need. I'm not an expert on communism, but I think Karl Marx would be happy to see individuals owning and controlling their own means of production without anybody forcing them to have to do something they don't want to do. Another cool implication, and the one I really am pretty psyched about, is that you can open source everything. You can open source the software, you can open source the hardware, and I believe that there's going to be a gigantic proliferation of open source hardware projects once we have this shared platform that you can use to build these things. Because if you make a design and you share it on the internet, other people need to have the same tools that you're using in order to build that design. So once we get to this point where there's some sort of critical mass of people with common machines that all sort of work in the same way, then we're going to see people designing open source robots, they're going to be designing open source machines that do useful things, open source toys, or pretty much anything that you can imagine that could be built by one of these machines. So, who's working on it? I tried to pick people that I thought were representative of sort of the state of art, what's going on right now. There's RepRap, which I like, and they're building an open source, self-copying 3D printer. The entire thing is open source from top to bottom. The designs, the electronics, the mechanical system, the firmware, the software, everything. There's another project called Fab at Home, which is a sort of CNC style machine, and they're also fully open source as well. There's these folks at Lumen Lab, which they released a really nice open source CNC machine. I was looking at it a few weeks ago, and they really did a nice job on it, so it's very good. And then there's also Fab Lab, which is sort of this MIT project where they take all this high-end digital fabrication gear that is usually like squirreled away in like research labs and government offices and big corporations that are willing to pay $100,000 for this equipment. And they just sort of ship them all over the world and hope that people do cool things with them, and which I think is, I really applaud them for doing that. It's a great little project. Or big project, I guess. And there's lots of other people working on this stuff. If you go online, there's a very nice growing open source hardware movement of people building and making and hacking. There are a ton of people working on this. They all have unique approaches, and it's still unclear which one's actually going to come out on top. The dominant project could be sitting in the head of anybody in the audience right now. And I hope so, actually, because if someone in here comes up with that magic idea that just like makes everything click, that would be very excellent. So if you have it, go work on it. I won't be mad if you leave right now. Of course, it's not all like flowers and sunshine. There are some things, there are some problems, but none of them are unsolvable. And everybody's that's involved is working on these things every day. And we need your help. If you know the answer to one of these problems, don't just tell someone about it, demonstrate it, prove it. Take an existing machine or technology, make it better, and show the world how you did it. We will all be richer as a result. So just to break it down a little bit, the first thing that's a problem is the technology is not widespread. It looked like a good number of people have access to CNC machines, which is very, very exciting to me. So the first thing we need to do is get more of these machines into the hands of the hackers of the world that are going to take them and they're going to do cool things with them, and then they're going to get other people excited, and then this thing will just sort of grow very naturally and organically. The second problem I